Thanks a lot, Ilya, for a nice introduction, and yeah, I thank the MLSS organizers for having me here. Actually, it's a full circle for me. Like 2007 was my first visit to Max Planck. I came here as an intern in Bernard's group, and then attended the summer school. And after that, I liked it so much that I think this is my fourth visit to MPI, and it's kind of nice. I mean, 10 years ago I was a student, now I'm here as a lecturer. Okay, so welcome you all for this lecture on kernel methods. Okay, so this is going to be the course outline. Okay, so as you see, there are 3 lectures. So the first lecture is now. The second lecture is today afternoon. I think it's at 3:30, and the last lecture is on Friday afternoon. Okay, so the course is now organized in this fashion, where the first lecture essentially I'm just going to talk about the folklore. I think most of you, probably the stuff that I'm going to talk here, I think most of you kind of know what's going on, but I will try to kind of do it and set up the notation, because we are going to kind of use everything else for the rest of the course. Okay, so this is something you can think of lecture 1 as something that's been done yesterday. And lecture 2, this is something that's kind of happening today, like in the sense this is some work that we have been doing for the last say 7-8 years. And lecture 3, this is something that's probably kind of going to happen tomorrow, like in the sense of this is something really new. So I'll probably talk about some work that's like just even a week's old. Okay. So one thing with this whole course is it could be like at some places mathematically demanding. So I'll try to kind of do it slowly. I know like most of you might have actually seen kernels, and especially if you are from a CS department, if you have taken courses, machine learning courses in computer science, mostly people, how do you say, they do kernels, but essentially I'm going to talk about here the function space. The function space point of view, it's not stressed that much. Usually we study like the feature space point of view, we invoke the kernel trick, and and go on and construct all these like fancy algorithms. So I'm going to impress upon the function space quite a bit in this course, because that is what is going to kind of help us to sail through the rest of the lecture. Okay. So moving on. So this is the outline of the first lecture. I'll start with some motivating examples. Very classical. We start with a binary classification problem. We'll then turn it into a nonlinear classification problem. So which is a very classical setting. And the second one is I'm going to give a brief intro to statistical learning, maybe over like 4 or 5 slides, to set up the notation, and then that will lead us to the function space point of view. Okay. And the key point of this lecture is studying certain things from the function space and the feature space points of view. The feature space point of view leads us to what is called the kernels. The kernels essentially lead to the feature space, and then we look at some properties of these kernels. And then we study what is called an RKHS. It's called a reproducing kernel Hilbert space. That's going to give us the function space point of view, and then we look at the properties of these two, and then we'll see that these 2 points of view are equivalent. And then we'll study the ridge regression problem, very classical, most of you know, but I'm essentially again going to do this from both the feature space and the function space point of view. The feature space will give you the kernel trick, the function space is done through the representative theorem, and then we'll see that these 2 things are equivalent. Okay, I mean, for some of you this could be just a walk in the park. It's not, probably you might have seen all these things, but it will be helpful to really set up the notation that you are going to use for the rest of the course. Okay, so here is a simple binary classification problem where we are given a bunch of training data, and we want to learn a function f such that we do well on the training data. Yeah. So here we have these 2 classes, and this problem is a very simple problem. You can actually see that the way the data is this is linearly separable. So the simplest of methods that one would try to use is just use a linear classifier. Okay, so why do you want to solve a simple problem using more difficult tools? So let's just start with linearity. So what does this linear thing say? I'm going to now choose my classifier of this form. So when we say linear, this is a function that's linear in x. Correct? So this is now parameters by 2 parameters, w and d. And all we need to do is find these w and d such that this relationship. So now there are many different linear classifiers. Okay, so you know one can use like a hard margin SVM, simple linear SVM. So you will basically get a maximum margin classifier. But then there are also like other methods. I mean, you don't, for this problem you don't even have to break sweat by going until SVM. You can simply do like a Fisher discriminant analysis, use superset, or you can use perceptron. Oh, okay, so there are many methods if you need to really solve a linear classification. But let us consider this problem where now this is a totally toy example, right? So here I have a real line. Now my blue points are in this interval between minus a and a, and the red points are in the interval minus b and b. I mean beyond b and less than minus. Clearly, I cannot use any linear classifier to kind of separate these two. Okay. But then we can perfectly separate these two regions by in general a conic section, but here I'm just using the circle. Okay, so here you can see that if I choose my function f of x is equal to x square minus r, then obviously for a certain choice of r, for x square less than r in this region, I say it's a blue, otherwise it's a red. So, so simply moving into like a quadratic form, I'm able to classify these two classes perfectly well. Okay, so let us write this as an inner product. If I write this as an inner product, all I'm doing is now this is my weight vector, and here all I have done is transformed my x to some phi of x. Okay, now phi of x, though my data is on the real line, I have transformed my phi of x to a two-dimensional vector. Okay, and by simply mapping my x to this vector, I have transformed a nonlinear problem into a simple linear problem. Right, so this is linear not in x, but it is linear in phi x. Right, and we call this phi x as a feature map. Okay, so we'll get more details later, but this is essentially the idea of kernel trick that probably you would have learned. You just take the data, transform into phi x, and then okay, hopefully the data becomes linear. You just lose your favorite linear. Here is another example, which is this XR problem. So again, in this case, there is no linear classifier that separates between these regions red and blue, right? But a conic section perfectly separates. Now, depending on how these classes are, how do you say, situated, you can probably use an ellipse, you can use a circle, you can use a hyperbola, or you can use a parabola, right? So depending on your data, you probably have like all these 4 different forms that could separate these classes. So this is the form of a conic section, and though this one is nonlinear. So by the way, here x is a two-dimensional vector. It's x1 and x2. X has like 2 components, right? And this conic section is in terms of these components x1 and x2. But I can still make this linear by mapping to this function phi x. Now phi x actually is in 6-dimensional. Right? So still the problem is linear in terms of phi x, but it's not linear in terms of my original vector x1, x2. Okay. So this is one part of the story. Okay. We'll now just change gears. Now we'll move on to something else. Now the motivating example that I'm going to give now, this will lead us to what is called the function space pointer. Okay, so I'm not sure whether you have seen some of these things in the learning theory course last week by Shai, or maybe you have already seen this before, but in any case, this is going to kind of set up for this. Okay, so the framework of statistical learning is as follows. So you have a training, let's say you are having a set D of input-output pairs, right, and these are given to you, drawn independently and IID from some unknown distribution P, and this distribution P is defined jointly on the spaces X cross. Okay, and the goal is you want to learn a map between X and Y. Okay, and you want to basically learn this map such that this f of x is a good approximation. So this is the classical problem. Okay, so if you need to know how good is your the function, the map that you are trying to learn between x and y, so you need to have a measure of the quality of approximation. So you define a loss on the space y, and the popular losses are, you can use like squared loss, hinge loss, and so on. Okay, so you define a loss function, and once you define a loss function, you define what is called a risk functional. Okay, the risk functional is nothing but it's basically the average loss. Okay, so the average loss is this. We call it as a functional because this is a function which is defined on this function, and it is a real number. Okay, such type of object we call it as a function, and this is defined as the expectation of the loss with respect to the joint density. Okay, so don't get scared. I mean, I might not use the expectation notation too many times. I mean, we are familiar with the symbol E. I might be using the notation just through the integral, okay, so that things are much more clearer. So all I'm doing here is you just take the average of the loss with respect to the joint probability. Okay, so now you have an objective. The objective is you have defined the risk functional. Now you pick your function f that minimizes the risk function, right? So that is a reasonable thing to do. So I want to pick an f star that minimizes the risk function. Okay, so now you are going to find this function f over the space of all variables, and this f star is called the base function. And so remember RLP. So to clarify, R is the risk functional, L denotes what is the loss that you are using, and P denotes that this is the expectation is taken with respect to the true probability measure. Okay, so I would call this as the true risk. Okay, and the true risk of my base function is basically called the base risk. Okay, so the base risk is the minimum possible risk that you would expect for a given loss over the class of all measurable functions. Okay, if P is known, this problem is probably not too difficult for certain loss functions. So if you use the square loss or if you use the absolute loss, you can actually find what this f star is. So this will be an exercise. If you haven't actually done this before, might be an interesting thing to actually check. You can actually exactly write what this f star is. Okay. Actually, I know yesterday in Steffi's lecture, she said she has given solutions, but I have not given solutions. If you guys have any questions, you can hit me, or you can catch me like that. Okay, that's fine. So if you know P, probably you can do something in some cases. But what if I don't know P? I mean, actually, in the learning setup, you really don't know P. The only way you know P is through the training samples that are given to you, right? So now using the training samples, the goal is to come up with f subscript d. So this is basically my estimator or a learner, right? So I want to construct. Okay, so the goal is to construct this FD such that the true risk of associated with an estimator is approximately close to the true risk of f star, which is basically the minimum possible risk. Okay, so which means my estimator is as good as the base. That's what this. And what is a universally consistent algorithm? Universally consistent algorithm says that as I see infinite number of samples, this quantity converges to the minimum possible risk, but this has to hold for every probability measure. Okay, and that's why the word universal. Okay, maybe, I mean, if this thing holds for certain probabilities and does not happen for certain probabilities, which means if you don't have a knowledge of your distribution, you might do very well. You might do very bad on certain data sets, whereas you might do well for certain distributions, right? But you don't want that. So you want it to do well for like every distribution, and that's why this universally consistent is a big deal. Okay, now this is again very classical. I don't know P, so but P is known through this data set D. So what I would do is, end of the day, this is what I'm trying to minimize, okay, but I don't know P. So I'm going to replace this P using an empirical measure. An empirical measure, all it does is it essentially puts equal weight on each of these endpoints, okay? And that gives you, so which means I'm going to approximate that expectation using this empirical sum. So we are going to see this trick throughout this course at many places. Okay, so wherever you have an integral, I just replace with an empirical sum. Now we call this as the empirical risk. Now here you can see that the subscript has changed from D to P to D. So this essentially says this is the empirical risk. Now you minimize the empirical risk. Okay, again you are minimizing the empirical risk for the space of all functions. Now is this a good idea? Not a good idea, because you can actually memorize it very well. So you can pick a function, for all your training samples, you basically say my response is yi, and elsewhere I don't even care, right? So you do very well on the data, but you can be very far from the truth, which is essentially the problem of overfitting. So that's the problem of overfitting. Now how to avoid overfitting? So this is called the structural minimization, where you don't optimize over the space of all functions, but you restrict yourself to a sizable class of functions, which I call it as script f, okay? And script f, usually you choose them to be the class of smooth functions. We'll see like why the class of smooth functions and how they arise here. Okay, so now I'm going to do this minimization over the script f, right? Now we have the total error. So this is my the true error of my estimator. This is the base. This I'm going to split into two parts. So one is the estimation error, which is called the variance. The other one is approximation error, which is the bias. So what is happening here? So this is the picture. The big circle is the space of all measurable functions. Script f is I have restricted myself to a certain suitable class, right? And here is my estimator, which lies within script f. Okay. Now this is the risk that is associated with my estimator. This is the base risk. And now you basically find a function which has the minimum possible risk within the class. Okay. Now this distance is the estimation error, which is approximation. So you can see that if f becomes larger and larger, the approximation error becomes smaller, whereas the estimation error becomes large, and vice versa. So there is a trade-off between these two errors, which varies with the size of this class. So the size of the class is pretty important. Okay, so I'm not sure again the learning theory whether you have seen the capacity and all those measures, right? So I'm kind of repeating the okay, so I believe like this would be something new. Okay, so this is my empirical risk. Okay, so f of xi, I'm just going to call this as delta subscript xi of f. Okay, so what is this notation? This says I'm going to define what is called an evaluation functional. Okay, again, the evaluation functional is something which operates on a function and gives me a number. Okay, so if I have an object which operates on a function and gives me a number, we call it as a function. So this is a functional. And the evaluation functional is basically defined as this operating on f, it simply gives me the value of the function at this point x. So that is how this function is defined. Okay, and therefore I can write f of xi as the evaluation functional of f, and this evaluation function is defined at x. Okay, so now we define what is called a bounded evaluation functional. A bounded evaluation, if evaluation functional is bounded, if there, sorry, this has to be mx, if there exists a constant x, m, such that this thing. So what is this telling? What this essentially tells you is this functional is continuous. Okay, so if I make small changes to this function f, the evaluation functional does not change by too much. Okay, the evaluation functionals are not always bounded. Example is the class of square integrable functions defined on AB. So you take the class of square integrable function. Okay, what happens is Okay, so let's say this is my square integrable function on AB. Okay, now you pick some point here and you essentially make the value here to be significantly large. Okay, when you take the norm of this function, the square integral functions are defined as a set of all functions defined between a and b such that the integral of f square is finite. Okay, so this is with respect to the Hilbert measure. Now, if you just change the value of this function at a countable set of points, this is not going to change, but obviously the value of the function has changed significantly. Okay, so the evaluation functional being bounded, it essentially enforces certain amount of smoothness of the function, okay, which is what actually you would want. Now there are, yeah.
It's a small detail, but why is m f by x that equation second?
Oh, this one?
Yeah.
Oh, because because this functional, it varies with x, right? Yeah, so which means, so here all I want is this thing is bounded by a constant which could depend on x, but times the norm of the function. Because it's not the same functional. At each point you are going to have a different function. Yeah, so I didn't mention this. Feel free to stop me if you have any questions. Okay. If I think the answer is going to take too long, because I don't have too much time, I'll take it up. Okay, so now there are various choices of f, which means now I'm going to restrict myself to class of functions with bounded evaluation functionals. Now these are some class of functions. Okay. Now what we are interested in is, if I choose f to be a Hilbert space of functions with bounded evaluation functional, okay, that leads us to what is called a reproducing kernel Hilbert space. Now one can ask the question, if I'm having all these choices, why should I actually care about this function, this space? Okay. If you work with these function spaces, it's not possible to get a simple, nice estimators, which you can actually implement in practice. I mean, they are much more complex than what you would get with an RKHS. Okay, so there are now two aspects, which is from the learning theory point of view, you want smooth functions, which is kind of ensured by all these classes, but from a computational point of view, RKHS play a significant role. Okay, so in many ways, RKHSs are a computational tool. I mean, you should think of them as something which really helps you in doing computation. It's not like you cannot solve these problems using other classes. You can. Okay, so there has been probably I think there is some citation about working with Lipschitz functions. So Ulrike von Luxemburg and Olivier Bousquet, they have some work published in JML or like 2004. So you can work with Lipschitz functions, but getting nice practical estimators, it's not easy. Okay. So summary, there are two ways to think about things. One is the feature map. All it does is you take a nonlinear problem, you're able to convert into a linear problem by doing this map. Okay. The second one is the function space. The function space is the one which actually talks about the statistical generalization. Okay, so you can get away by not even looking at the function space, just caring only about the feature map. Okay, and you can work with kernels. You can do all fancy. But you will never have an idea why these things work unless you understand the function space point. So the function space point of view is pretty quick. Okay. Okay. A short history. Please don't think that kernels actually came into picture only in machine learning. Okay, I mean this thing has existed since 1900s. Okay, so this is introduced obviously in mathematics, particularly people working in partial differential equations. So this has been introduced by Stanislav Zaremba, and then a lot of work has been done by all these people, mostly by Arenzon when this theory has matured by 1950s, and then this was picked up by Emmanuel Parson. So apparently there is a kind of a nice history where Emmanuel Parson, when he was a PhD student, I think at Berkeley, So he got an exam paper, and the question actually dealt with reproducing kernels, which was not actually taught to them in the class. And this was something that was just given to them, and he figured out about RKHSS by the exam question, and then he started doing his research on that. Okay, so this was the work in statistics was started by Emmanuel Parson and then picked up by his students, and a lot of work was done by his student Grace Wahba, who is currently at the University of Wisconsin at Madison. But somehow the statistics community, they didn't seem to have picked up, paid that much attention to the kernel literature. Probably there are very handful of people working on kernel methods in statistics. And interestingly, by the time she probably finished like most of her significant works, the pattern recognition and machine learning people seem to have picked it up. I mean, by 92, this was like the important paper by Poser, Gohan, and Wapnick. And since then on, there has been a furious activity on kernel methods in machine learning. I must say, now in the learning community, probably there are only a handful of people actually doing kernels. I mean, particularly the kernel theory. I mean, there are a lot of people still doing kernel applications, but I would say the kernel methods, probably they are not as famous as it used to be. Now with all the advent of deep learning, I think all is taking backseat. Okay, there are also other areas where kernel methods have been used, like signal processing, control. There's the French school around like 70s and 80s. They have done a lot of work using the RKHSS in probability theory, stochastic process, and so on and so forth. But the main contribution of machine learning or pattern recognition community to these kernel methods is the feature space point of view. So most of these communities have worked with the function space point of view, but the feature space is somehow pushed by the machine learning community. Okay, so now let's dive into the first topic, which is studying. Now I have said like, okay, you have the function space and the feature space point of view. Now I'm going to talk about the feature space point of view. The discussion that I'm doing here, it's completely based on chapter 4 of this book. I mean, I pretty closely follow chapter 4 of this book, giving the required details and kind of removing the details that's not needed. And the last slide of this lecture, I have given suggested references, some of the books, depending on your interest. If you are more interested in a statistical aspect or a mathematical aspect or a machine learning aspect, so there are some interesting books you can check out. Okay, so again, most of you would know this. This is again to just set up the notation. We first start with the definition of an inner product. An inner product is a bilinear form. So this is, if I have a vector space, the inner product takes 2 arguments. It gives me a real number. Okay, for the purpose of our course, I'm just going to deal only with real numbers. It can also give you complex numbers. Okay, so there are 3 properties. One is that object is linear in the first argument. I mean, it doesn't matter. You can also take it linear in the second argument, but to fix our convention, we say it's linear in the first argument. It is symmetric, and it is positive definiteness. So we'll also see positive definiteness later in the course, and please do not confuse that positive definiteness with this. But this property is also called as the positive definiteness of this bilinear form. So all it says is the inner product is always inner product of an object with itself is always non-negative, and it's 0 if and only if the object is 0. Okay, and this is the definition of a norm on this vector space, which is induced by this inner product. And if I have an inner product space, we call it as a Hilbert space if that space is complete, and complete is a kind of a technical operation where you add like certain things to that inner product space and it becomes complete. Okay, so we just call it as a Hilbert space. Okay, so what is, first of all, this inner product gives you a notion of similarity between objects. Oh, that's right, thank you. So there should be a square, there is a square root missing. Thank you. Okay, so this is a measure of similarity, right? Why? Because if I take the distance between 2 say objects f minus g, from that definition this is f minus g, which gives me, so it's kind of good to do this because we'll be doing something like this in the second lecture. Okay, so this is minus fg minus gf plus gg. So this is my norm square of this plus norm square of g minus 2 times fg, where we exploit the symmetry of the inner product. So here you can see that if f and g are close by, this norm is going to be small, okay, and therefore this inner product is going to be large. So that basically says if f and g are similar, this is going to be large. If f and g are dissimilar, this is going to be small. So you can use inner product as a measure of similarity, or essentially as a degree of similarity or dissimilarity between objects. Okay. Okay. So now what is a kernel? A kernel, it is a bivariate function. It has 2 arguments and gives me a real number. I call a bivariate function as a kernel if there exists a map phi. This phi is a map from x. I'm going to just call it as an input space from now on. It's a map from the input space to a Hilbert space H. Okay, so there exists a map phi and a Hilbert space H such that I can write this bivariate function as this type of an inner product. If I am able to write it in this fashion, I call such a bivariate function as a kernel. Phi is a feature map and H is a feature space. Okay. The first thing is, if I give you a kernel, which means there exists some phi and H, these phi and H need not be unique. So you can simply take this simple kernel, kxx prime is xx prime, right? So you can have one feature map to be a simple identity map. I can also create another feature map like this. Here x is an element in R, here this whole thing is an element in R2. Okay, so you can have multiple feature maps and multiple feature spaces yielding the same kernel. Some properties, so here I have also kind of given the proofs of these things. Okay, so any scalar multiple, any positive scalar multiple of a kernel is a kernel. So it's very easy to check. A conic sum of kernels is a kernel. So these properties are useful, okay, because if you have access to a function which is a kernel, you can use that to generate different kernels. Okay, so all these properties help you to generate new kernels from old kernels. Okay, so what is a conic sum? If I have a collection of kernels, then for any collection of positive numbers, the linear combination of the kernels is called a conic sum, and we are saying this conic sum is also a kernel. Okay, so this is easy to do. The only technical point here is this notation. So how many of you are familiar with the direct sums? So all we are doing here is once we have written this inner product with respect to HI's, I'm saying I can write it in this fashion. All we are doing is we construct these feature maps by stacking the feature maps of all of them. Okay, and this gives me an interpretation of what is called the direct sum. What this direct sum essentially says is, if we take an element in H tilde, that element in H tilde can be decomposed as elements in each of them. Okay, so for example, in this notation, you can say the direct sum of the real line and real line gives me R2, right? Because if I give you a vector x comma y, I can write that as x comma 0 plus 0 comma y. So I have now decomposed into 2 elements where they belong to real. But the difference of kernels is not a kernel. Okay, so this is in general, so this is not a kernel, whereas the product of kernels is a kernel. Okay, so this stuff I'm going to go slowly because this is super critical in lecture 2 when we study what is called a covariance operator. Okay, so if I'm having 2 kernels K1 and K2, the product is a kernel. So how do you do? So, okay, before I get here, let me give you a bit more explanation. So let's say K1 is a kernel that is defined on this set. and K2 is a kernel that is defined on this set. So I believe you agree that K1 times K2 is now defined on the product set. Okay, so K1 times K2 is now defined on these ordered pairs that is generated by this product. Okay, so which means now the resulting kernel is going to have like 4 arguments. Okay, so that's why I write like this. Okay, so this is my resulting kernel. This is the product of kernel. Now here, this kernel, because this is a kernel, there exists some feature map phi1 and a feature space h1. I can write it in this fashion. Similarly for K2, and I can write it in this fashion. So what does that notation mean? So let's understand this. So let's say h1 is simply R2 and h2 is R5. Okay, let's just study this in the setting that we understand well, and then we essentially see what that notation is, because in lecture 2 I'm going to use this significantly and I'm not going to repeat. Okay, so this is what it means. Now because we are in the Euclidean space, I can write this inner product using this transpose. Okay, this is a scalar and I can take the trace, and trace you can permute elements. Okay, so by permuting entries, so by moving this to here in the trace, I'm going to get like this. Right, so now what is this? This is a matrix from R5 to R2, and this is a matrix from R2 to R5. Okay, so this is a matrix. Okay, so let's take, yeah, so this is a matrix from R5 to R2. This is also a matrix from R5 to R2. I'm doing now inner product on the space of R5 to R2 matrices. So you know that is basically your Frobenius inner product. Okay, so the notation that I have here, this is basically the tensor product. All I mean is the outer product of vectors here. Okay, so similarly, and this tells me that this is basically the space of 2 by 5 matrices. Okay, so we can understand this thing easily in Euclidean spaces, but when you move to general Hilbert spaces, okay, we cannot basically write all this transpose and stuff, and that's why we directly use this tensor product notation. Again, all this tensor product notation essentially tells that this is, when you're in the Euclidean space, you say it's a matrix, but when you move to Hilbert space, you just call it as an operator. Okay? So this is simply the outer product between this. I mean, this is some element in Hilbert space. This is some element in Hilbert space. This is outer product between those elements, and this outer product is nothing but an operator. Okay, so you are simply taking the Frobenius norm between those operators. So here you have established that there exists a feature map like this and a feature space like this, and therefore K is a kernel. Okay, so for any arbitrary function, if I have a kernel K in this fashion, so this is also a kernel. So this property is pretty useful if you need to actually prove that a Gaussian kernel is indeed a kernel. Okay, so it's not easy to show otherwise. I mean, so this is a useful property to show that Gaussian kernel is a kernel. And this says the kernel function along the diagonal is always non-negative, and this is the Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality. So here, because K is a kernel, so you have this inner product, and by applying Cauchy-Schwarz, we get this, and this thing is nothing but the square root of the kernel and the square root of the kernel. Okay, standard. Okay. The next thing is you can have the feature map which could be infinite dimensional. So let's say I define a kernel in this fashion. Okay, so again a bit of notation. This notation says I have a sequence phi i's which is indexed by the index set I. So I is some set, and little I takes values in this I. And L2 of I is basically the space of square summable sequences. So it is defined as the sum of phi I square of x, and this is the norm with respect to this L2. Okay, so if I have a bivariate function like this, that bivariate function is also a kernel. In fact, if I is countable, then the feature map that I'm constructing here is going to be an infinite dimensional feature map. Okay, so this is one can also do something like that with a Gaussian kernel. Okay, and you will see that in the case of a Gaussian kernel, the feature map is an infinite dimensional. Okay, now we can use these properties to verify that the popular things that we usually consider they're all kernels are indeed kernels. So polynomial kernel. Okay, I mean you can take these things as an exercise. I have given hints. To verify that this is a kernel, just use binomial theorem. Once you use binomial theorem, use the sum and product rules. The sum and product rules that I have shown you before. If you choose c is equal to 0 and m is equal to 1, we get a linear kernel. Now for the exponential kernel, let's use the Taylor series expansion of the exponential function. We get this. Now you use again the sum and product rules, and here you will see that the feature map is infinite dimensional. Now for the Gaussian kernel, I have written it in this fashion. So this is precisely of the form f of x kxx prime f of x prime. Okay, we have just established that the exponential function, this one is a kernel. So this is a kernel, and this is some f of x and some f of x prime, and therefore the Gaussian kernel is a kernel. Okay, so this is a simple way to show that the Gaussian kernel. Okay, so that's nice. But the question is, if I give you a bivariate function, okay, it's not possible in many cases. You are going to, I have given you 2 exercises later, okay. There's no way that you can show that those 2 functions are actually kernels by establishing that there exists a feature map and a feature space such that I can write it in this fashion, okay. For some functions, you can prove that they are kernels by finding what this p and h are, but in general, it's not easy. Now, how do I say that if I give you a bivariate function, how do I know that that bivariate function is a kernel? This complete characterization is provided by the Moore-Arens-John theorem. What this theorem says is if I have a bivariate function, that function is a kernel if and only if it is symmetric and positive definite. Okay. So what is symmetry? That if I simply exchange the arguments, nothing changes. And positive definiteness is this quadratic form is non-negative, right? We call that a kernel is strictly positive definite when this quadratic form is 0, only when all the entries, if the quadratic form being 0 implies all these alphas are 0, okay, then it is strictly positive definite. Okay. Kernels are symmetric and positive definite. So if I need to prove this result, one direction is trivial. Okay, so if I know that a function is kernel, it is symmetric and positive definite. Very easy. Because of the symmetry of the inner product, the kernel is symmetric, and here you can, for the positive definiteness, you can write it in this fashion, and one direction is trivial. So if I tell you that a function is, the bivariate function is a kernel, then the kernels are symmetric and positive definite. But we are not in the game. I mean, I want to really check whether a function is a kernel or not. I don't even know whether it's a kernel, right? So we are actually interested in the other direction. That if I give you a positive definite function, we need to show that it is a kernel. This is totally not trivial. Okay? This proof is based, in fact, it is based on the construction of an RHS, which essentially proves this result. Okay, that's okay. Now one can ask the question: how easy it is to check that a bivariate function is positive definite? That itself is not easy. Then you are like, okay, you wanted to check something is a kernel. You said it is a kernel only if it's positive definite, and then you are saying I cannot even check positive definiteness. What are you doing here? Okay, but for positive definiteness, you can do something. Okay. So now we are going to consider a special class of functions called or special class of bivariate functions called translation invariant. Okay, I'm going to now restrict myself to my domain to be RD, and I'm going to consider kernels of this kind. Okay, kxy is equal to c of x minus y, where c is a positive definite function. If c is a positive definite function, then k is a positive definite kernel. Okay, you can just check this in the quadratic form that I wrote before. For this class of functions, there is a beautiful result by Bachner, where the result by Bachner gives you a complete characterization for positive definiteness of translation invariant kernels on RD. What this result says is, if I have a positive definite function c on RD, this is positive definite if and only if I can write this as a Fourier transform of a positive measure, a finite positive measure. For all practical purposes, you can think of this lambda as just a probability measure. Okay? If this is a probability measure, all you are doing is just computing the characteristic function of probability measure, and you know it's positive. Okay? One direction, again, proving one direction is easy, proving the other direction is hard. Okay? We are not going to get into proof. But this result is super powerful, and we'll also use this result in the second part of the lecture, second part of the course. Okay? Usually people use the notation I. We are using I at too many places for too many things. I'm just going to do like square root of -1. So it's a complex number. Okay. Now here is the program. If I give you a function, right, a translation invariant type. Okay. Now if I want to check whether it is positive definite or not, all I have to do this. Okay. We are considering that first of all the function c that I gave, just check whether it is integrable. Okay. Then simply compute the Fourier transform of that function. The Fourier transform of this function c, I'm going to denote this as c hat. Okay. Now let us check whether the c hat is non-negative for all points in RD. Okay. If that is the case, c is positive definite, and the corresponding kernel is, and the corresponding bivariate function is a kernel. Okay. So I hope you kind of follow the reasoning here. The reasoning is, the previous Moore-Aronson theorem says if a bivariate function is a kernel if and only if it's positive definite. Then I am using translation invariance and applying Bachner's theorem, which says a function is a translation invariant kernel is positive definite if and only if it's a Fourier transform of a non-negative measure. So to check whether something is positive definite, just take its Fourier transform and check whether the Fourier transform is non-negative. If it is the case, it is a kernel. If it is not, it is not a kernel. Okay. And now here is your exercise. Show that this one is positive definite, whereas this one is not. Okay. So you take the Fourier transforms of these two functions. You check that the Fourier transform is positive, but here the Fourier transform at some points is negative, and therefore this is not positive definite, and whereas this is positive definite. Okay. So this will be good time to do some integration. Okay. So what have we done so far? We have shown the equivalence between the kernels and symmetric and positive definite functions. Okay. So that is one part of the story. We'll again come back to this part of the story after doing the function space point of view, and here we are going to deal with reproducing kernel Hilbert space. Okay. So here is the definition of a reproducing kernel Hilbert space. H is a Hilbert space. The critical thing is it is a Hilbert space of functions. Okay. So previously you had all these feature maps phi, right? So we said phi x is also an element in this Hilbert space, but phi x need not be a function. It can just be a vector, right? So, but what we are interested in here is it should be a Hilbert space of functions with a bivariate function k, okay, where this bivariate function satisfies these two properties. What are the properties? This one is, if you take the value of this bivariate function at any point. This, by the way, if you're not, I hope like, I mean, you're familiar with this notation. All I'm saying is k has 2 arguments. I'm basically fixing the second argument, keeping the first argument floating. So this itself is a function. It's a function of the first argument, right? So now this function lies in that Hilbert space. And if you take the inner product of this function with any other function, I get back the value of the function. So if these two properties hold, then such a kernel is called a reproducing kernel, and the corresponding Hilbert space is called a reproducing kernel Hilbert space. Okay, so at this point, I mean, it will all look like mumbo jumbo, but we'll see, I mean, what nice properties this function space has. First of all, the reproducing kernel is a kernel. Correct? Why? Because you take this property, you choose your f to be some k dot y. If you choose your f to be k dot y or k dot x prime, I'm taking this inner products, which means I'm computing now the value of k dot x prime at x, which gives me this, and therefore I have established a feature map and a feature space, and therefore k is a kernel. Okay? From now on, we are going to call this feature map px, which is k dot x, as a canonical feature map. Okay? So for the rest of the course, wherever you see a canonical feature map, all I mean is my phi x is k dot x, and your canonical feature space is your RKHX. Okay, so we have established that a reproducing kernel is a kernel, and we know that kernel is symmetric and positive definite. We have shown that before, and therefore every reproducing kernel is symmetric and positive. Now here comes the main property, which is what actually we started with when we did this motivation through learning theory. We want these evaluation functionals to be bounded, correct? Now you look at the evaluation functional, delta x of f. This is simply the value of the function at x. Use the reproducing property, we get this. Now use Cauchy-Schwarz, you get this. Now this quantity is nothing but square root of kxx times the norm of f. Okay, which is nothing but the evaluation function is bounded or it's continuous. Okay, so this has that property. Okay, so this essentially is the real quick summary of RKHS. What this is telling is, if I have a Hilbert space with a reproducing kernel, it is an RKHS. This is by definition, right? The converse is also true. So what is the converse? The converse is that every reproducing kernel Hilbert space has a unique reproducing kernel. Okay, so this is critical. So what we are saying is, if I have a reproducing kernel, corresponding to that reproducing kernel, there is an RKHS. Okay, you might wonder, maybe there are multiple reproducing kernels which give the same RKHS, and that's not possible. Okay, if I have an RKHS, it has a unique reproducing kernel. So what does that mean? That means there is a one-to-one relationship between reproducing kernels and RKHSs. So if you define this, this is automatically defined. Or if you define this, this is automatically defined. So you don't have too much room to play with. Okay. Now this is the Moore-Arensdawn theorem. Yeah.
So this is just a terminology question. What is the definition of reproducing kernel?
The reproducing kernel is, it satisfies these properties. You take a Hilbert space, and if the bivariate function satisfies these properties, it's a reproducing kernel. Okay. Did I answer you? Yeah. Okay. So the Moore-Arensdawn theorem says, if a bivariate function, if I have a bivariate function which is a positive definite kernel, then there exists a unique RKHS with that kernel as the reproducing kernel. Okay, so in fact this is the theorem which ties everything. It says the Moore-Anderson theorem essentially is telling that the positive definite kernel, if I have a bivariate function which is a positive definite kernel, okay, it is also a reproducing kernel. And I know there is a one-to-one map between reproducing kernels and RKHS. Okay? And RKHS, the reproducing kernels in RKHS are also kernels. So that's how this entire loop is kind of completed. So all this equivalence is pretty critical, because if you know that a function is positive definite, you are done. Previously, using Bachner's theorem, we are able to verify some conditions based on which you can verify whether a bivariate function is positive definite or not. If I know it's positive definite, then just use this. I know it's a kernel. I also know it's a reproducing kernel, and there exists a unique RKHS. Okay, maybe I don't know what the unique RKHS is. Okay, but actually that's not even needed. You don't even have, for all the machine kernel learning algorithms, you don't even have to know what the RKHS is. That is the beauty. All you need is positive definite. If you know something is positive definite, you are in the game. Okay. So this is a proof which I'll skip. Okay. So now this is RKHS. Now what happens? So what type of functions lie in this space, right? So this one is simply the restatement of this proof, the construction of the proof, and if you restate it, this is what it happens. What this tells is the functions in this RKHS are nothing but the linear span of the kernel functions. So the kernel functions play the role of basis functions in the RKHS. Okay. So here is an example where if you have a Gaussian kernel, the functions are in this space. They are of the form which is the linear combination of these kernel functions. If you use a Gaussian function, you have a Gaussian bump at each xi, and then if you sum them up with some factor alpha I, you are going to get this blue function which also lies in this space. Okay. So this slide is pretty important. Okay. I mean, I'm not giving many details. I'm totally summarizing the theorems from Steinwart's book. In many of these theorems, proving one direction is simple, proving other direction is not at all simple. Okay. But what is the crux of the slide is the properties of the kernel completely control the properties of the Hilbert space. Every function in the space is bounded if and only if the kernel is bounded. Okay. If the kernel is integrable, every function in the space is integrable. If the kernel is differentiable, every function in the space is differentiable. I mean, the differentiability of functions in the space, the order of differentiability is controlled by the order of differentiability of the kernel. Okay. Every function in the space is continuous if and only if this k dot x is continuous for all x. So the nice thing about all these properties is if you pick a kernel, the kernel completely determines the properties of the functions in the space. You really don't have to care about what really happens in the function space, because everything is encoded in the kernel. Okay. Okay. So until so far, okay, we looked at some properties of these RKHS, but if you really want to understand what happens in this space, again, we need to go back to the simple setting of your input space being RD and the kernel being translation invariant. So the translation invariant kernels on RD, they are pretty powerful if you need to do anything mathematically to understand what is happening with these spaces. I mean, again, we'll keep getting back to this setting even in lecture 2. Okay, the translation invariance is very powerful. Okay, so bit of notation, but we'll go over this slowly because this is what is really important when we want to really understand the smoothness classes which we covered in the learning theory part. Okay, first let us assume that the kernel is integrable. Okay, I just need this assumption because the Fourier transform of the kernel exists. Okay, I'm going to denote C hat to be the Fourier transform of the kernel. Okay, now a notation L2 of RD, it contains all those functions which are square integrable. Okay, so this basically says, obviously, I mean, the function f cannot decay to infinity much slower. I mean, there has to be some rate at which it has to decay to infinity such that this integral is well defined. The result is I'm quoting this result from Wendland's book. I also mentioned this in the suggested reference. Oh, maybe not. Maybe I forgot. Okay, so let us define this Hilbert space H. Now this is a set of functions in L2 such that this integral is finite. Okay, so here f hat denotes the Fourier transform of the function. Okay, and this Hilbert space is endowed with this inner product, where this line, it denotes the complex conjugation. Okay, because the Fourier transform can be complex. Okay, so you can, at this point, you'll see like, okay, kind of what's happening. So let's try to digest this. First of all, to understand what I wrote in the previous slide, let's understand what happens with Fourier transforms. Let's say this is a function, and I've added some noise to this function to get this function. Okay, let us take the Fourier transform. So the Fourier transform of this function is this. The Fourier transform of this one is this. Okay, so as you can see, this is a smooth function. Because I have added noise, this is a rough function, which means this has high frequency components than this one, which is denoted by the Fourier transform. So here you can see the Fourier transform beyond this point essentially does not have any frequency components, whereas in this case you have still some frequency components in this region, right? Because there is some signal strength in this region. So the signal strength in how do you say, for large values of your omega essentially denotes your signal is noisy. It's not smooth, correct? Okay. Now, if the function is smooth, as I said, it does not have any components, high frequency components, which means the Fourier transform, it quickly goes to 0. Whereas in this case, it does not. Okay. How slowly it goes to 0 determines how rough this function is. So there is a relation between the smoothness of the function and the rate of decay of the Fourier transform. If the Fourier transform goes to 0 very quickly, the function is very smooth. Otherwise not. Okay? So using this, let us understand this. For this, we'll consider Gaussian kernel. Okay, Gaussian kernel is a translation invariant kernel. You can take the Fourier transform of this Gaussian kernel, which is also a Gaussian function. Okay, in fact, actually, proving this is not that easy. So that's why I didn't give this as an exercise. Though Gaussian kernel is pretty popular. Okay, the Fourier transform of this is this, which is also Gaussian. Now let us plug in this C hat. So we have seen this is my Hilbert space. The Fourier transform of the kernel is in the denominator. So let us just plug that in. If I plug that in, this is my Hilbert space. Okay. So now what is this one telling us? So here I am looking at the set of functions which are square integrable such that this integral is finite. Here I am taking the Fourier transform of the function, squaring it, and multiplying by this exponential function. As you can see, as omega goes to infinity, this function grows really, really fast, right? So this function grows very, very fast, but still I want this integrable to be finite. For this to be finite, I want that this f hat of omega, it should go to 0 pretty fast. It should in fact go to 0 much faster than this stuff, right? Now if this thing is going to 0 very fast, as we saw in the previous picture, the corresponding function has to be really smooth, because what is this? This is the Fourier transform of the function. If the Fourier transform of the function goes to 0 very fast, then the function has to be very smooth. Okay, so which implies the rate at which my Fourier transform of the kernel goes to 0, it determines the rate at which the Fourier transform of it determines the smoothness of the functions of the function. Okay, so that's why if I have a fast decay of my Fourier transform of the kernel, it says my corresponding RKHS is smooth. Okay, so let us define this as the norm of the function in this Hilbert space. Okay, you can verify that this is a norm. So because you can verify that this is an inner product, and therefore that basically forms a norm. Okay. So instead of me wanting that this integral is finite, suppose say I want that this quantity is less than or equal to some alpha. Okay. Does that enforce more smoothness? Right? It should. Because if I'm saying my norm is less than some alpha, okay, which means I need to have these functions go to 0 even faster such that this norm is less than alpha. Okay. So the smaller the norm of the functions, the more smoother are the functions that I'm considering. Why is this needed? This is what really that you would use in your kernel methods, right? So you have okay, so we saw that in these learning theory things, we saw that this is your space of all functions, and then you want to pick some f. Okay, so f is a class of smooth functions. What we are going to do is we are going to choose this class of smooth functions to be some RKHS. Okay, but in practice you don't choose the entire RKHS. What you would start with is you choose a small ball within the RKHS. Okay, and then you keep increasing the size of this ball. Okay, so we'll see this later. Whenever you are doing this regularization, all this regularization is doing is you start with a small ball. You have the regularization parameter lambda, right? You might have seen this in ridge regression, SVMs, and everywhere. You usually cross-validate. That parameter lambda, it determines what is the size of the ball that you are considering. The smaller the size of the ball, the more smooth the functions are, right? Because you are not allowing the norm to be much larger, and therefore you are enforcing more smoothness. Okay? Yes. It's differentiable. Yeah. So in this case, okay, so that's a good question. So the question is about what do I mean by smoothness? What do I mean by like the functions are so many times differentiable and so on and so forth? So let's go back to this one. So here I am saying my Hilbert space is the linear span of these basis functions, right? So which means the functions in this space, they look like this. So you can already see from that definition that if my kernel is a Gaussian kernel, I know the Gaussian kernel is infinitely differentiable, right? So that automatically tells me that the functions in that space are infinitely differentiable. Okay. So in the case of Gaussian RKHS, of course, the functions are going to be infinitely differentiable. But then the bandwidth parameter, the variance of the Gaussian, it plays a role, right? So if you have a bandwidth parameter which is okay, in my case, let's see, in my case it's gamma, right? Yeah, so gamma is the bandwidth parameter. So larger the gamma, which means this function is growing much faster, which essentially makes these functions to decay much faster. They have to decay much faster, and therefore the functions are more smoother. So even though all Gaussian kernels for any bandwidth are infinitely differentiable, the choice of this gamma is critical. If gamma is large, those function spaces are smaller than the function spaces with smaller gamma. Okay. So if I need to elaborate a bit, so if I take h gamma 1, if I take h gamma 2, for gamma 2 greater than gamma 1, h gamma 2 is contained in h gamma 1. Okay, though these are all Gaussian kernels, right? Everything is infinitely differentiable, but the bandwidth parameter plays a huge role. And that's why when you do your learning, you cross-validate over gamma as well. Like where does you really want to live? Okay, so that enforces your smoothness. Yep. No notion of smooth. There is a notion of smoothness because when I said here the fast decay and the smoothness, right? When I say the rate of decay, it relates to the smoothness of the function. If you want to really make it formal, the rate of decay could be like 1 over omega to the alpha. That basically says my smooth function is like alpha times differentiable. Okay, so I am kind of skipping the math here, but essentially when I say smoothness here, all I mean is there is a differentiability, and that differentiability is determined by the rate at which this Fourier transform decays. Okay, so now let's consider another example. I call this as a Sobolev architecture, where the kernel that I'm considering is a Laplacian kernel. Okay, it's a Laplacian kernel on the real line. Okay, I'm not considering the usual Laplacian kernel where you have the L1 norm and x and y lie in Rd. Okay, so this is Laplacian kernel on the real line. The Fourier transform of this can be shown to be like this. You can verify that this function is non-negative and therefore this is a positive definite kernel by Bachman's theorem. Okay. Okay, so now just apply. If you remember, the c hat was in the denominator, correct, as before, and therefore now this is the Hilbert space that I'm considering. As you can see, compared to the Gaussian case, this function, this is not growing that fast. The Gaussian case, the function was growing exponentially faster, but here this is only growing quadratically. Okay, which means for this integral to be finite, this function has to obviously go to 0, but it need not have to go to 0 faster than what it was the case in the Gaussian. What does that say? It says the functions in the Sobolev space, they are not as smooth as the functions in the Gaussian space. In fact, the functions in the Gaussian space are contained in the Sobolev space. Okay, so in fact these functions, they are only 1 times differentiable. Okay, so whenever here I'm talking about the smoothness, there is this notion of differentiability that is hidden there, and that notion of differentiability is related to the rate of decay of the Fourier transforms. Okay, so again, if you restrict yourself to the small balls, then you are going to get like more smoothness. Just a comment: if you extend these kernels, I mean, if you extend these things to Rd, you get a family of kernels called a Mattern kernel. And it indeed corresponds to what is called a Sobolev space of certain smoothness. So this is not required, but I'm just kind of introducing you to a new kernel called a Mattern kernel, of which a special case is the Laplace kernel. Okay, so summing up, we have looked into all these notions. We started with a kernel, which is a bivariate function, and we said a bivariate function is a kernel if there exists a feature map and a feature space. And then we said it's not always easy to check whether a bivariate function is a kernel, and then we gave the characterization that a bivariate function is a kernel if and only if it's symmetric and positive definite. But again, we don't know to check for positive definiteness, but we assume that if a kernel is translation invariant, we used Bachner's theorem to check when it is positive definite. Okay, so that is the feature space part of the functional feature space part of the story. And then we constructed this RKHS with this as the canonical feature map. And Moore-Armstrong theorem establishes the equivalence between the kernel's RKHS and positive. Okay, the key point is the properties of the kernel control the properties of the RKHS, and RKHS, depending on the type of kernel you choose, the RKHS contain certain type of smooth functions. Okay. So now let's put this into action in the ridge regression setup. So I'm going to do ridge regression. You probably know this, okay? But nevertheless, I mean, we are going to do. I mean, I already have the slide. So okay, let's do this. First, we do it from the feature space point of view, and then we'll also do from the function space point. Okay. For the feature space point of view, for the time being, I mean, you might even Okay, so this is basically I'm choosing a square loss function, and I have to minimize this. So here is your the penalty, lambda is the regression parameter. Okay, so at this point I have not even motivated you saying why should you even use the ridge. Okay, I can give you an explanation here, now, right now. Okay, but we'll really see why you need the ridge. Okay, so all I have done is I have written this in the matrix form, and I believe every one of you know how to obtain this W by solving this problem. Okay, if not, please take that as an exercise because this is like really fundamental. Okay, so let's say W, you have this W. Why do you need this lambda? You need this lambda because you are taking the inverse of this matrix, and if this matrix, if this is not a full rank matrix, okay, because X is from D by N, so this is a D by D matrix. So if this matrix is not rank D, okay, then you cannot invert. So from the point of view of inverse problems, to make this problem stable, you can always add this penalty. Okay, but we'll also see why you need this penalty from the statistical learning point of view. Okay, and I'm going to call this as my primal problem. Okay, now this is one thing that you can do beautifully in the ridge regression, which probably may not happen in like many other algorithms like SVM, which is this inequality. This equality is easy to verify. Okay, so here the key is XX transpose. I am basically writing it in terms of X transpose X. This X, which is post multiplied, is now pre multiplied. Okay, this is just easy to check. Okay, so now I'm going to write this quantity in this fashion. Okay, so just pre-multiply here by the inverse of this matrix. Okay, and post-multiply here by the inverse of this matrix, and then I can write this problem in this fashion. Okay, so all I have done is written two different variations of finding this vector W. I call this as a primal form, I call this as a dual form. Okay, it's probably not going to matter much in the case of a linear regression setup, but when you do the kernel regression, this plays a this is a big deal. Okay, so here this is a D by D matrix, this is an N by N matrix. Okay, and if you want to predict, you compute the because I am saying my f of t is of the form. So this f is of the form W comma this. I'm just going to say this is how I'm going to predict. So this is the prediction in the dual primal. This is the prediction in the. Okay. The key is we just have to look at how does this matrix X transpose X look like. The X transpose X is basically the matrix of these inner products. The matrix of inner products, we call it as a gram matrix or the kernel. I don't call it as a kernel matrix now because we haven't seen kernel yet. Yeah.
It's very specific prime that relate quality in offsets, say states or.
So, I mean, if you are familiar with SVMs, so usually there is a certain problem that you solve, which people call it as a primal problem, and then use a Lagrangian duality to get an equivalent problem. We call that as a dual problem. Here, I move from primal to dual, okay, by simply using this trick. This is all the primal to dual actually happens in the ridge regression. You don't have to, I mean, if you want, you can also, I mean, if you had a constraint, you can basically write a dual problem and do everything, okay? But instead of really bothering about all those things, I want you to just show this equality, and all you need to go from primal to dual in the ridge regression is just this equality. That's all it is to it. Okay, so this is the linear regression. Okay, so now if I want to do nonlinear regression, remember the motivating example. The motivating example is you take your point, you map it to some feature space Px, and just do linear regression, right? So that's what we did there. So all I'm going to do is map my point to a feature space, just do linear regression. Okay, so this is what is usually called the kernel trick. whatever linear method you have, just replace x with cx and just keep going. Okay, at some point you are going to see what you are going to see now, and boom, so you have everything works out. Okay, so let's do this. If you do this, this is exactly the same of the previous slides where I have replaced x with p. Okay, so now again this is the primal, this is the 2. Okay, but this is not as easy as it is in the linear regression case. Okay, first of all, now you are taking the inversion. The size of this matrix in the previous case is d by d, but the size of this matrix here is the size of the is basically the dimension of your Hilbert space H. Okay, so this, as we have seen, we can have feature maps which are infinite dimensional. So this could be like infinite dimensional. First of all, I'm not completely rigorous here because I should not actually use the transpose. I should put like a tensor outer product, okay, like a tensor product. But again, I didn't want to do that here because, okay, I'm doing this feature map on the matrix. It's not completely rigorous, but you can kind of understand. If you need to do it correctly, you need to introduce like some more notation which I don't want. But to drive in the idea, all I'm saying here is this operator or this matrix could be potentially infinite dimensional. Okay, and I'm taking the inverse of that. Now write it in the dual form. If I write it in the dual form, this is what I'm getting. Now look at how does this matrix look like. As you can see, this matrix is just of size n by n. Nothing has changed compared to the linear regression to the nonlinear regression. It's still n by n. If you look at this, this is again the matrix of inner products. But this matrix of inner products is between these feature maps. Okay. Now if I define these matrix of inner products as a kernel, okay, so I can now replace all these things with the evaluation of the kernel at points xi and xj. Even in the case of prediction, I have a prediction in the primal form, I have a prediction in the dual form. Okay, prediction in the dual form, it depends only on the inner product between this px and pt, which is again a vector of inner products between the feature maps, which again results only in the kernel evaluation. Okay, what is this telling? All this is telling is if I have access to a kernel, okay, all you need is just compute the values of the kernel at my training points and compute the values of the kernel between the training points and some test point. That's all I need to do. I don't have to care about what this feature map is, what this feature space is. All those things are immaterial. Okay, and that is the beauty and power of the kernel methods. Okay, so until this point I have not done anything about the function space. I don't know what really is happening. I mean, if you apply this kernel ridge regression in practice, it does really well. But why does it work? This formulation does not tell you anything. Why does that work, right? This is totally a computational trick where I can do nonlinear thing, in fact, by going into infinite dimensional space, but really not even knowing what that space is. All I really care about is just this kernel function. Yeah. So this is what I summarized here. The primal formulation, in fact, requires the knowledge of the feature map and the feature space. If I need to do anything in the primal, it doesn't have a simple formulation like that in the dual. I have to know what this phi and I have to know what this Hilbert space H is. Okay? Whereas in the dual, I really don't need to know anything. All I need to know is you define the kernel and everything is taken care of. Okay? If you do linear regression, the linear regression is simply working with the linear kernel. Correct? Okay, and this is exactly what is called the kernel trick. The kernel trick is, again, as I said, it's computational. It does not tell you anything about the statistical properties, why it works. If you need to really know why it works, you have to get back to the function space point. Okay, and this has kind of created a cottage industry in machine learning, say in 2000s. You take any linear algorithm, you do this kernel trick, and then you get kernel variations of all these methods. So if you're interested in algorithms, and if you haven't looked at any of the kernel literature, I would suggest looking at the book by Bernard and Alex. And this has like a host of algorithms. Okay, in lecture 3, we will do kernel PCA, and there I will probably do that in a slightly different way than what's been done. Okay, so probably you will learn like another trick, like hopefully you have learned something in the ridge regression setup from primal trick. Okay, so if you can, I mean, if you want to do this in the examples that we saw before, so we saw that this is the feature map, and if you apply the kernel trick with this kernel, because for this feature map this is the kernel, then I'm just going to, if you apply linear classification, if you apply linear, how do you say, if you apply simple any SVM or any binary classification using this kernel, I'm just going to separate those points. And similarly here, the exercise is, for this problem, you find out what is the kernel function that you have to use. Okay. Okay. So I really have 3 minutes. Let's see how far I can go. I probably have like. Okay. So ridge regression. Let's understand this from the function space point of view. So this is a just a recap of the terminology, right? So you have the empirical risk. I cannot minimize empirical risk or class of all functions. I need to restrict myself to subclass of smooth functions, and the choice of f. You want that this choice of f has bounded evaluation functionals, and what we are going to do is pick this f to be an RKHS, because for RKHS I know it has bounded evaluation functionals, and I'm now going to pick this f to be the set of functions in the RKHS whose norm is less than or equal to alpha. Okay, as I said before, you can do this whole thing. For bounded evaluation functionals, there are also other classes like Lipschitz functions. Okay, if you're interested, you can look at this paper by von Luxemburg and Buski. So, kind of getting efficient algorithms is not possible. Okay, whereas the kernel method gives you efficient schemes. Okay, so as I was explaining in this picture, I'm going to now minimize this over, this is my class of functions over which I'm going to minimize my empirical risk. Now you apply the Lagrangian formulation, and that is how you end up getting this factor of lambda. Okay, so this is how the ridge penalty kind of appears in the picture, because you, as I was telling you before, the smaller the alpha, the more smoother the functions are, right? But if your class is too small, then you are going to have a huge approximation error. Okay, so the way you would do, actually, the intuition is, if I see more and more samples, you have more information. Then I can slowly increase the size of the class. Okay, so as you see more and more samples, you slowly keep increasing the size of the class. That is the only way you would get universal. You will get consistency. If you fix your size of the class with the sample size, you are never going to get a consistent estimate. Okay, so the choice of lambda determines the smoothness of the functions. But here the problem is you are doing an optimization for possibly an infinite dimensional function space. As in the case of Gaussian, we saw it's an infinite dimensional space. So here it's no more like a simple optimization problem as in the linear regression. You have an optimization over infinite dimensional space. Now this is a beautiful result due to Kimmeldorf and Wachba, and also kind of generalized by Schulkopf. What it says is, if the solution to these type of problems, okay, if I'm minimizing this over functions in an RKHS, the solution, it always has a form that it is a linear combination of kernel functions computed at my training sample xi. Okay, this is a really powerful result, but the proof to say is really trivial. And what is the power of this result? All this is saying is, now if I have to look for functions in the space, I just look for only these type of functions, and therefore the problem reduces from solving an infinite dimensional problem to a finite dimensional problem, because now I have to only look for n parameter. The proof is really trivial. All you do is you choose h to be the direct sum. You say h can be written as a direct sum of h naught and a space that is perpendicular to h naught. H naught is chosen to be the span of these kernel functions. By the direct sum, it says if a function lies in this space, I can write this as a sum of functions in these two spaces, where f naught and f perp are perpendicular to each other. Okay. Now let us look at your loss function. The loss function has f in it. The regularizer also has an f in it. In the loss function, it is f of xi. Use the reproducing property, f of k dot xi. Now f is f naught plus f perp of this form. Okay, but this is 0 because this is perpendicular to this, which means this is perpendicular to all these functions, and therefore this is 0. So which means computing the value of the function at xi is same as computing the value of f naught at xi. Okay, but on the other hand, for the penalty, because of this form, the norm of the function is always greater than or equal to the norm of f naught. Okay, and therefore the solution has to lie in this place. Okay, the proof is really trivial for the depth of the result actually it gives. Now we use that fact. Now we know from the representative theorem that f is a linear combination of these kernel functions. You put that back in, and I'm going to get this linear problem. Now I'm just going to solve for this alpha. Okay, so the solution to this problem is, again, you get like alpha hat is this, and if you want to predict, the prediction is this. You can actually go back and check the solution. This is exactly same as the solution that you had got with the feature space pointer. Okay. But you see, I mean, the feature space point of view gives the same solution without no intuition. Okay, not really knowing kind of what's happening. But this one, it kind of tells, saying, okay, so this is the solution, this is my estimator, but then behind it, there is a very strong theory which essentially says why these things could lead to generalization. Okay, how to choose H? So this is a big question. You have all these RKHSs, and I know there is a one-to-one relationship between RKHS and kernels, correct? Now, can I use a polynomial kernel? Okay, the result here is, if you need to do anything reasonable in a learning theory setup, right? If I want my approximation, so this is like the best error in the class, and this is the Bayes risk. If I want my approximation error to be 0, okay, you cannot work with any RKHS that you want. There is a certain type of an RKHS that you need to work with, and that RKHS is called a universal RKHS. Where in the case of a universal RKHS, what it says is, if my Bayes risk, say, is a continuous function, I can approximate my Bayes function. I can approximate my Bayes function by any function in the by some function in the RKHS arbitrarily well. Okay, so that is what this is saying. A kernel is said to be universal if the corresponding RKHS can approximate any continuous function. Okay. Now to verify that something is universal, you can show that a kernel is universal if and only if this is strictly greater than 0 for any finite sign measure mu. Okay, so this is a much stronger notion than strictly positive definite. So we saw positive definite, we saw strictly positive definite, but you want something that is more stronger than strictly positive definite, it is universality. Okay, and we will see, this is a nice point actually to stop, because this is pretty much the place where we'll pick in lecture 2, and we are going to see objects of this kind. But the crux of the story here is, if you need to do anything reasonable in terms of consistency, you have to work with infinite dimensional spaces. You cannot work with polynomial kernels. Polynomial kernels are finite dimensions, and they do not satisfy this property. Okay, so you have to work with infinite dimensional spaces. Okay, so that's the end to the lecture 1. Here are some references. So anything that you see in magenta in the slides it's all the references which I've given here, but these are my suggested readings. I have segregated in different topics. Like if you're interested mainly in like algorithms with some theory, you can refer to these textbooks. If you're really interested in the learning theory point of view, these books are great. I mean, this book is fantastic. If you really have to know deeply about the properties of kernels and then like how they affect the generalization performance and stuff, this book is fantastic. And from the statistics point of view, you will see very non-standard applications that we really don't see in machine learning. If you want to really see those problems with very nice theory, this book by Berlinet is great. Wagbaugh's book is a classic. It's still like slightly old. And then if you want to really have a more rigorous introduction to theory of architectures from a mathematical point of view, this is a very recent book. Okay? Thank you. See you guys now.